I'm Dave Katz. I'm a software engineer at Juniper Networks. I did 5 years at Cisco before that, and I was at Merit before that, so pretty much anything you've ever run into you can blame on me. I'm going to talk about ISIS and OSPF and talk fairly technically about what's the same about them, what's different about them, and as providers, what that should mean to you. Start with a little bit of history. For those of you who aren't as gray as I am, this will seem fairly ancient. For those who are around, shout me down if my memory is bad. A whole bunch of nuts and bolts about how little mechanisms in these protocols compare to one another. A bit about scalability, which is everybody's favorite paranoia in routing protocols. Some pragmatic considerations on choosing protocols, and finally some conclusions. This is from memory, and it's been a long haul, so if the dates are off by a year or two, I'm real sorry. Back in 87, DEC brought what became ISIS into ANSI, which is the American part of ISO, as the protocol for OSI, and it was actually the DECnet Phase 5 protocol. It did CLNP, which was the OSI IP, and that's all it did. The next year, this thing called NSFNet Phase 2 happened, and it was 1/3 of a T1 built out of great big piles of IBM RTs. It needed an IGP, so Yakov found an early draft of ISIS and wrote a routing protocol. Around the same time, OSPF was starting in the IATF because people thought they needed a link state protocol. RIP wasn't really going to take us too far into the future. So they actually grabbed the ISIS spec and started with that because link state protocols are notoriously hard to do well. So to their credit, they took one that was likely to work and based on that. And one very cold December in Ann Arbor in 88, excuse me, a bunch of the usual suspects got together and said, hey, we could extend ISIS for IP, just slap some TLVs in there, it'll be great. 89, the OSPF RFC was published. Proteon, remember them, started shipping OSPF. ISIS was moving along in the ISO standards body. And I think it was the Honolulu IATF in 89 where there was much sort of public shouting about dual ISIS and OSPF and which one should go forward as a standard. And so the IATF blessed them both as standards going forward, but OSPF is preferred. And meanwhile, behind the scenes, all the right people were talking to one another, and so there was lots of stealing of protocol features going on behind the scenes. 90, the dual ISIS RFC was published. 91, the next OSPF spec was published. Cisco shipped OSPF in 91, I believe. And there was also ISIS for OSI only shipped that year. 92, there was a partnership between DEC and Cisco, and they made this cute little router about the size of a VCR tape. And it was running Cisco software, but it needed to support Phase 5 DECnet. So Cisco started shipping IP-capable ISIS at that point. And OSPF, meanwhile, was taking off everywhere, and nobody was using ISIS. 93, this is the foreshadowing part. Novell published a spec for a routing protocol for IPX because IPX RIP wasn't good enough. They had made a couple of stabs at defining a link state protocol for IPX, but link state protocols are notoriously hard. So they got smart, took ISIS, changed a couple of things that Neil didn't like, published the spec. The next year, Cisco shipped NLSP. But since NLSP was so much like ISIS, it was decided that rather than having two separate implementations of almost the same protocol, there would be one implementation with 10 or 15 places where it says, if NLSP do this, if ISIS do that. As a side effect, most of ISIS got rewritten. And about that same time, this concept of a large ISP started popping up, and people like you, Nat, and MCI were knocking on our door saying, what IGP should we run? And since ISIS had been recently rewritten at the time, and since there had been some interesting field issues with OSPF, and we said, let's use ISIS, it'll be great. There was also this NSF mandate that you had to support CLNP, but And that's the revisionist history that everyone uses for why everyone's running ISIS now, but it really didn't matter that much. 95, the ISPs started deploying this stuff. You went through the usual cycle of panic and disaster and repair, and things stabilized pretty nicely. ISIS continued to spread within the niche because people looked at UNet and said, well, their network seems to be working, let's do the same thing that they are. And so it sort of snowballed. Within the niche, ISIS became fairly popular, and in fact, some people started switching from OSPF because they wanted to be like the big guys, so they decided to run ISIS. Interestingly, it became a barrier to entry for people building routers, which it was not intentional at Cisco to choose ISIS because no one else had it. But as it turned out, it was a handy way of keeping the riffraff out of the router market. Going forward, well, you can read this back, it's not that hard. Other folks started shipping. Juniper shipped in hardware in '98, I think. Now, both protocols have continued to be extended. Traffic engineering is probably the most notable extension to both protocols going forward. And here we are today. The two protocols are really, if you stand back far enough, they look a lot the same. And this is not too surprising because they started from the same place. They're both link state algorithms. In a link state protocol, each router distributes its local neighborhood and floods it within the area or within the network. And everybody ends up with a map of the whole network. And then you calculate routes based on the map you have. They both have a two-level hierarchy. In OSPF, you have the backbone area and non-zero areas. In ISIS, you have level 1 and level 2. Pretty much the same thing. They're both deployed for some value of widely deployed, and there are multiple interoperable implementations of both. Now, OSPF, if I had to characterize each one, OSPF is optimized. There was a lot of hand-wringing back in the late 80s about we want this to be as lean and mean and so directed toward IPv4, and we want all the mechanisms to work just perfectly and to make the adjacencies come up just a little bit faster. And so there's a lot of sort of tinkering kind of complexity in OSPF. ISIS is a lot simpler. On the other hand, it was not originally designed as an IP protocol, and so there's some weird clunkiness to it, like you have to assign OSI addresses to your IP-only routers. Encapsulation, sort of from the bottom up here. OSPF runs on top of IP, which is the way IP routing protocols have traditionally been done. One of the side effects is you can have virtual links. Since you're sending IP packets, you can send an OSPF packet from here to the other side of the planet if you want. The downside of that is it also means that people can launch OSPF denial of service attacks at your network. Since you're just sending them through IP packets, you can lob them in. If LSAs get really big, you use IP fragmentation to make them fit. One of the supposed advantages of the IP encapsulation is you can use VC-MUX endcaps on ATM, which is basically a null encapsulation. Everything on your VC has to be IP. So if you're running OSPF, you turn off all of your encapsulation, then you can fit your TCP ACKs in a single ATM cell, and it'll buy you a 30% bandwidth gain or something on your ATM network. ISIS, on the other hand, runs directly over layer 2, sort of architecturally next to IP. And to me, this always made more sense because routing the protocol your routing protocol runs on top of always seems slightly strange. But it does mean that you can't do virtual links without doing true tunneling to do things like partition repair. And there is something in the spec for it that I think only Jack ever bothered to implement. And it's certainly not deployed. The fact that it doesn't run on IP means it's fairly difficult to spoof because there's no way to get an ISIS packet into the inside of your network from the outside because it's not an IP packet. So unless you accidentally leave a GRE tunnel open or something, you can't do it. It does require snap encapsulation because it's not an IP packet, and so you lose your 30% overhead in your ATM network. But Hank Schmidt came up with this cute hack where you just look at the first byte, and if it says 40 through 4F, it must be IP. If it says 81, it must be ISIS. And this is, in fact, the way you discriminate protocols in OSI. So it's somewhat ironic. But that's a whole lot easier than trying to run ISIS on top of IP, which there is a draft spec for that doesn't seem to be garnering much interest because there's an easy hack to make it work. Both of them support LANs and point-to-point links in pretty much the same ways. ISIS does not have an NBMA mode, non-broadcast multi-access. So there's no specific support for things like frame relay and ATM. If you want to use those networks, you can either model them as a LAN and expect full connectivity, fully transitive connectivity, or you model them as a set of point-to-point links, which is what they really are. But ISIS relies on the operating system to do that for you. So in Cisco parlance, you have to have point-to-point sub-interfaces in order to make ISIS work safely, because trying to run it as a LAN is just insane. There's an NBMA mode in OSPF in the original spec, which is, it takes a whole lot of configuration, and you're still out of luck if you lose your link to the designated router. There is a more recent draft, I'm not sure what the standardization status, but it's widely deployed, the point-to-multipoint mode, which essentially implements point-to-point sub-interfaces but does it inside the routing protocol. So if you have an operating system that can't do virtual interfaces, or if there's too much overhead and you don't want to generate a separate sub-interface for each of your 500 ATM circuits, point-to-multipoint can be handy that way. Packet encoding, the amount of hand-wringing in 1989 over how the packets should look was really amusing. There's just, 32-bit alignment was the holy grail, and there was much arguing about what was most efficient. And we're not talking about switching data packets here. These are relatively sparse control traffic. But should the bits go on the left side of the word or the right side of the word? So you came up with really nice pictures and it looks great in the spec, but it really accomplished nothing else. But what it did not accomplish is extensibility. All the fields are positional. You can't sort of add an extra thing onto the end of router LSA because you found of an interesting thing that you wanted to extend it with. You can't do it. So you can extend LSAs by using opaque LSAs, but you can't extend hellos. So if you wanted to say support IPv6 in OSPF, you have to rewrite the protocol, which is what they did. Let's see, and unrecognized LSA types is thrown on the floor, so you can't really add new LSA types either. Opaque LSAs were added a few years ago, and enough people support them now so that they're likely to get from one side of your network to the other. ISIS, on the other hand, is TLV encoded. So there's a field that says type, and then there's a field that says this is how long the data is, and then a bunch of data. The nice part about that encoding is that you can skip those and go on to the next TLV if you don't understand the type. So the spec says if you don't understand a type field, you skip it and go on. So it provides you a crude hook for extensibility. And you can extend all of the packet types because they all have TLV encoding in them, which is how you manage to, say, make hellos carry IP address information. It's just throw another TLV on the end. You can nest TLVs in theory. You can define a TLV which is defined as more TLVs inside it. So if you want to create a structured piece of data, you can do it. That doesn't exist in the base spec, but a couple of the recent extensions are encoded that way. And OSPF uses the same concept in the traffic engineering extension. So the nice part about that is you can add things to the traffic engineering part of it in the future and still be backward compatible in theory with earlier versions that support traffic engineering, or backward compatible with versions that don't support it at all. Both protocols support areas and a two-level hierarchy with a blob in the middle and a bunch of blobs attached to the edges of it. This reduces the route calculation on each router because it doesn't see all of the detail of the entire network. It just sees the detail of the areas that it's connected to. In OSPF, the area boundary is in the middle of the router, so you assign on an interface-by-interface basis which area the interface is going to go in. ISIS, on the other hand, the area boundary is on a link rather than in the router. And people find this really hard to picture. And it was done this way not so that you could have lots of areas, because the idea was you didn't have very many areas, they were going to be big, and what you want to be able to do is merge them and split them apart as your network changed. So as it turns out, most people can't seem to picture this in their heads. And that makes it fail my test for is this deployable. There are some people starting to look at multi-level ISIS, but there hasn't been much need for it because even in the largest core ISPs, they've been running one flat area and it seems to work just fine. Now, database granularity is probably the key design difference between ISIS and OSPF. And a lot of the details of the way the protocols unfold are driven by this. Now, in OSPF, the idea was an atomic hunk in your database should be as small as possible. So if you have 10,000 externals in your OSPF domain, there are 10,000 little LSAs, and each one is a separate thing you can look up in the database, and each one is a separate thing that has to be sent and acknowledged. And the idea was that if you have that fine granularity, then if you have, say, one external out there that's flapping, then you just send this little update with a one LSA in it for each flap. Now, network and router LSA, since there's only one router LSA per router and one network LSA per LAN, those things can get arbitrarily large. So as it turns out, since people don't usually put lots and lots of externals into their OSPF domains, you tend to end up with a few fairly large LSAs anyhow. When it's time to flood these things, you build update packets out of multiple LSAs because they may be really small, but you want to send big packets. So there's a bunch of complexity in deciding how to build an LSA update when you send it. And since each router is generated separately, the packet that goes through the network changes at each hop. It gets bigger and smaller, and the contents may change because each router has a different view of what needs to be forwarded. ISIS, on the other hand, the database is built out of link state packets. So each one is a bundle of stuff. And the originating routers can build them however it wants. So it'll throw links between routers and externals and stubs and whatever else you want, any way it wants into this hunk. And that hunk is what gets flooded and what you can look up in your database. And each of those is flooded intact from hop by hop across the network. So the LSP that one router generates is exactly the same LSP that will show up on the other side of the network. What that means is that LSP has to be small enough to fit through any link in the network. So the size of an LSP is an architectural constant, just essentially 1500 minus a few bytes. The downside of this is that if you have if you have this 1500 byte LSP and there's one piece of information that's changing in the middle of it, you keep sending the 1500 bytes. As it turns out, the 1500 bytes don't matter. It's the packet count that matters. If you look at the cost of processing incoming, the overhead is the packet rate, not the number of bytes. You can throw away the bytes pretty efficiently if you know what you're doing. And you can also do things like notice that a few things are flapping and move them off to their own little LSP, since you can pack them any way you want. I don't think anyone's been crazy enough to try to do that because it doesn't really matter. But you could, in theory, make it even more complicated. When each of these each of these protocols brings up neighbors, you send hellos, and each hello essentially has an I heard you mechanism to establish two-way communication. There is a settable rate at which you send these things and a settable rate at which they expire, because if your router crashes, you wait the dead time and then you declare the other guy to be down. In OSPF, all of the holding timers and hello intervals have to be identical on a subnet. And if you try to change one of them, then those hellos are lost, and it's very difficult to actually change your hello timers without disrupting your network. If you change them all in less than 40 seconds, then the network would stay up. But you have to type really fast or have really scary scripts. Let's see. Right. ISIS, there's this funny padding stuff, which has caused nothing but grief. And the idea was to detect links that were less than 1500 bytes, of which there are very few media in the world that have smaller MTUs. So the idea was that in some cases you pad these out to MTU size, and if the other side can't receive them, then you probably don't want to bring up that link because the LSPs won't be able to make it across. Because remember, they may be 1500 bytes, you can't fragment them, they're always the same size. As it turns out, this is useless and has caused nothing but support calls and has never done anything good for anybody. So you don't actually have to pad them, and nobody should be checking on the receive side to see whether anything is padded. So in fact, you can decide not to pad them, and no one should care. So in some cases, we're only padding to 1500 rather than to MTU. If you're still trying to bridge FDDI to Ethernet, some people were trying to do that, and wondering why the adjacencies wouldn't come up in one direction. That's why. OSPF, there's now a check in the database exchange for MTU matches, and you'll get stuck in XStart state if your MTUs aren't set the same. And the reason they have to be the same is the guy who's creating the link state update packet may build it to MTU size on a link basis. So if one guy thinks the link is 4K and the other guy thinks it's 1500, and the guy at the 1500 end can't receive jumbograms, then your network is in a world of hurt. Now, when neighbors first come up, you have to synchronize databases because the whole algorithm is based on everybody has the same information. And essentially what you do is you say, here's everything in my database, and in one case, your neighbor will figure out what you're missing and send it to you, or in the other case, you figure out what you're missing and ask him for it. But that's essentially the way the process works. But the granularity of the database is a huge issue here. In OSPF, you may have literally tens of thousands of items that you have to synchronize between adjacent routers because the granularity is very fine. So there's this amazingly complex and frankly brain-dead protocol for synchronizing databases. It's weird. It's window size of 1 and master slave and all this stuff. And the idea was you synchronize the routers, but you don't want to move traffic across the link until the databases are synchronized. So there's all these phases that you move through, and you don't declare the link to be up until you reach full state. And that way you don't end up blackholing traffic. And a lot of the complexity of OSPF is tied up in this whole database exchange process. And it's really a side effect of the granularity, and it takes a whole bunch of DVD packets going back and forth to list all of these LSAs in your network. ISIS basically says, flooding is what synchronizes databases, so we'll just turn on, plug in, and the right thing will happen. And things will become synchronized. Now, and this is easy because remember, LSPs can be big, and there aren't very many of them. And so it doesn't take much to say, this is what my view of the world looks like, because there aren't very many items in it. So in a couple of packets, you can describe your entire database. So there are things called complete sequence number packets, CSNPs. And if you're really worried about transiting traffic before you have the full picture, there's a really great hack. There's a bit called the overload bit, which is really there to say, I've run out of memory, I don't have the whole database, please don't forward packets through me. And everyone calculates SPF around the router. Well, what you can do is turn on the bit when you're booting up and kind of wait around and say, well, I haven't seen any new LSPs for a while. I must have everything, and turn the bit off. Since it's probabilistic anyhow, that's probably a good thing to do, and it's about 10 lines of code. But that's not what the bit was for. But there's a whole bunch of opportunistic hacks in ISIS that ISIS happen to turn out to be really handy that way. Both of them have this designated router concept on LANs. And the idea is if you have 10 routers on a LAN, if you just did hellos and brought up adjacencies, each of those 10 would have an adjacency to the other 9, and you'd end up with order 100 adjacencies and order 100 entries in your link state database. And so a designated router is elected, and it models the LAN as a node, and everybody is adjacent to the LAN. So in the case of 10 routers, you have 10 adjacencies to the LAN. They both use the same concept. OSPF, they wanted to optimize, they want to minimize the failure time if the designated router fails. Partly because there's so much overhead in becoming adjacent because you got to toss all those DVD packets back and forth. So you define a backup designated router, and it knows to jump in if the main designated router goes down. Furthermore, they didn't want the DR to hop around. If a new guy came in and said, my DR priority is higher, the OSPF designer said, well, we don't really want that guy to become DR because it'll disrupt the network. And so the DR ship sticks to the last guy that got it. And so this is not disruptive, but it's also non-deterministic. If you've ever played with a network and tried to make a particular router your designated router, you'll find that it's arbitrarily difficult with OSPF. And the algorithm is fairly complex and hard to understand. In ISIS, everybody just says, I'm adjacent, because there's so little overhead in synchronizing databases. So you don't, in OSPF, you're only adjacent to the designated router and the backup designated router, and to nobody else on the LAN. And ISIS say, we're adjacent. There's a DR election, a really simple, stupid DR election scheme. If the DR dies, there's no backup DR, so everyone has to elect a new one. The overhead of doing that is really just the time to detect a DR has failed, because everybody is already synchronized, so there's no huge database exchange thing to go through. It's deterministic because it's based first on the priority that you advertise in your hello, and second by the highest MAC address. But if you don't really want the DR to hop around when the new guy comes in with a higher priority, there's a hack in NLSP where you say when you become DR, bump up your priority by 20 points. And that effectively makes it sticky, and it's 5 lines of code. And it's once again an accident of the design of ISIS. It certainly wasn't thought of that way. LAN flooding. Everybody likes multicast packets on LANs because they're so wonderful and they save so much. But if you're sending a multicast and you have to get unicast ACKs back, you've saved half of your packets. And half is not an interesting number. Unless you're so bandwidth clogged that you can't even support the protocol on the LAN, in which case you're so dead because you can't even move data. Saving half the packets is really an uninteresting optimization. There's a whole bunch of per neighbor state because you have to keep, if you're flooding it, you're a DR and you're flooding it to 100 routers, you have to maintain state for each of the 100 routers as to who needs to have a retransmission, who's active, and so on and so forth. Then there's a bunch of acknowledgement suppression stuff because they wanted to optimize the packet count, even though they weren't optimizing the packet count. So there's some tricks for not acknowledging under certain conditions. There's a whole bunch of mysterious rules in the acknowledgement scheme. But it's also not that exciting. And in particular, the more routers you add, the more flooding traffic you get. It grows as the number of routers because of the ACKs, essentially. ISIS has actually a fairly cool scheme, which is whoever has a new LSP multicasts it on the LAN, so everybody receives it. And there's no acknowledgement. And instead what happens is the DR periodically multicasts his view of the world. And if everybody agrees with his view of the world, then nothing else happens. If one of the other guys says, hey, the DR is missing something, he'll send the LSP to the DR. Well, he'll flood it on the LAN and everybody will hear. And if the DR, if someone says, boy, I'm missing something the DR has, then you can send a PSNP, which is essentially a request for the LSP. So once you're synchronized, under normal circumstances, the flooding traffic is constant regardless of the number of routers, because there's one flood and there's one DR sending CSNPs no matter how many neighbors you have. There's still hello traffic, so it's not completely flat. But in flooding, it's flat. So it's really cool, but it doesn't matter because nobody puts hundreds of routers on a LAN. So, oh well. One of the big complaints about ISIS is that in the base spec, link metrics are 6 bits wide. Which doesn't give you a lot of granularity for trying to map them to link speeds and that sort of thing. The reason that was done is there's an optimization you can make in the route calculation that will remove an order log n out of the cost of the calculation. But CPUs are really fast, and LSPs, SPFs, even in the biggest networks, seem to take on the order of milliseconds. And so, it's fairly pointless, but it did make it really hard to assign meaningful metrics. So there's a wide metric extension, which is now broadly available in your favorite vendor's routers, which expands them so that they're as big as, or maybe bigger than OSPFs, and you can do all your favorite metric games with it. One of the other complaints about ISIS is that they went full the other way from OSPF in terms of how much information went into level 1 areas. In OSPF, the default is you send everything into non-zero areas, so you have optimal routing. You don't have all the complexity of the topology outside the area, but you have each individual route so you know the best exit point from the area. In ISIS, they went full the other way and said, the only thing we'll advertise into level 1 is default. And you go to the nearest level 2 router, and follow that out to the world, and that may not be the optimal exit path. As it turns out, people really, really like optimal exits from their areas. So there's a route leaking extension to ISIS now, so you can in fact leak your level 2 routes into level 1 and get optimal routing out of the area. Both protocols support MD5 authentication. Use it wisely, particularly with OSPF, because I can launch OSPF packet bombs at your network. You'll hopefully be packet filtering on the edges of your network and throwing away all OSPF packets that are coming in from the edges. And that's probably, you want to do that in addition to cryptographic, because I can still send 100 megabits of OSPF packets with bad checksums on them and kill your router. And IGP hacks are really, really dangerous. If you're lucky, your whole network melts down. And if you're unlucky, someone is clever enough to subvert it. That could be very interesting. There are MPLS extensions to both protocols, and in fact, they're identical. The idea is you're carrying around this extra link information. How much bandwidth is available on this link? What policy color is this link? And you use the routing protocol as a mule to carry all this data around. And then there's a separate traffic engineering module, which is not part of the protocol, which looks at this database and says, oh, I want to set up the other LSP, overused terminology, from one end of the network to the other, and it can find its path with the right policy and so on and so forth. Since they're independent of the protocols, they are absolutely identical by design. So these two extensions are in lockstep in the IETF. Scalability. Everybody worries about scalability, but nobody does anything about it. Scalability is almost a non-issue in terms of what the protocols are capable of. We'll get to the one case where it's actually interesting. In theory, your OSPF topology is limited by how much you can stuff in a router LSA, because each router gets one router LSA. It can't be bigger than 64K because that's as big as an IP packet can be. So you can get about 5,000 links in it. So it's hard to imagine a router with 5,000 neighbors, but I've seen routers with 400 neighbors, so an order of magnitude doesn't take that long. But it's kind of pushing it in other ways as to whether this is in fact practical or sane to have a topology like that. Externals and inter-area routes are essentially you can have have billions of them until you run out of LSA IDs. In ISIS, you're limited by how many LSPs a single router can issue. And each router can issue 256 LSPs of nominally 1,470 bytes of data. And you have to pack everything you want to advertise into that much. And that, in fact, will not, if you were foolish enough to dump full BGP routing into ISIS, you will run out of space about 10% of the way into the, into the redistribution and not be able to advertise the rest. You can, in fact, come up with various interesting hacks like having a fake LAN, topology that'll look like a LAN, and all you do is create this AirSat LAN that has a zero cost link to you, and then you get another 256 LSPs, and you can do up to 256 of those. And if that's not enough, you can act like two routers and that are adjacent to one another, because you can just lie through your teeth in what you send out to the rest of the network, and as long as you act like what you're advertising, then no one can tell. But at the end of the day, if you have an even slightly sane network, none of this matters. You shouldn't run out of space. This one's a little bit more interesting. When you flood an entry into out into the world, it has a lifetime. And if your router crashes, you've sent all this stuff out into the network. If you die, eventually all of the information you flooded will die by itself. But since it dies by itself, if you're still alive, you have to keep refreshing it so that it doesn't die when you don't want it to. In ISIS, there's a lifetime field, which says, this is how long I want this LSP to live. It's 16 bits wide, and it's in seconds, so you get up to 18 hours. And on a one-by-one basis, you can pick this and send it out. And as long as you refresh it in 18.68 hours, you're fine. In OSPF, for some reason, they decided they wanted to count up rather than down. So the field in OSPF is the age. And you set it to 0 and you send it out, and then it counts upward. And since you haven't told anybody how long it should live for, there's an architectural constant which says 1 hour. And 1 hour seems like a long time. But if in fact you redistribute full routing into OSPF, you'll be refreshing on average, if you smooth it perfectly, every 23 milliseconds, just in refresh load with nothing interesting happening in the network. Now, of course, doing that is crazy, but there is a do not age LSA, which is created for the demand routing stuff, which in theory you could press into service, where you can send it out and it just lives forever, and you throw it away if connectivity to you fails. But that's not backward compatible. You can't, if you deploy this in your network today with implementations that don't support it, your network will get weird. So you can't really get there from here unless you want to cut over your entire network. But at the end of the day, if you don't do something stupid, it shouldn't matter. So don't do anything stupid. Now this is the only interesting issue, is what's the load of flooding? And it's only interesting if you have one of these networks that is a full mesh of ATM or frame relay VCs, and a number of large ISPs have built network with hundreds. So with 300 routers, you have 90,000 links, and each of them is a point-to-point link. And when the flooding algorithm says, when you receive a new LSP or LSA, you flood it out every other interface you have. So if you have 300 routers, something happens, the one router sends it to the other 299 routers. Each of those says, oh, this is new, I need to send it to the other 299 routers. So boom, boom, you get n squared copies of it. And each of those is order n in size because it's typically the router LSA or the LSP, which gets bigger with the number of routers. So if a link fails, you get order n cubed information banging around. Now if a router fails, since you're adjacent to everybody, all of the other routers have to flood their router LSA or LSP again. So then you get order n to the fourth information hammering around. And in fact, a number of, probably around 96, this started to become a serious problem. And we came up with a hack in ISIS. It just happened to be built in such a way that you could just kind of not bother to flood it out of a bunch of your links, and no one would notice. And since you could, in theory, partition your flood, what you're doing is creating a flooding topology by hand. And you could, in theory, partition that, but you can send CSNPs periodically, which will heal all of the partitions. So it's an awful hack, but the entire world is depending on it right now. OSPF, there isn't any way to do this without changing the protocol. The ISIS hack is completely backward compatible. The guy at the other end doesn't have to know you're doing it. And so this is really the only serious scaling issue in any of these protocols, and it's only serious if you have a really crazy network. Pragmatism. The OSPF spec reads really well, and if you want to implement a protocol and you don't really know much about routing protocols, if you pick it up and do everything that it says in the order that it says, you're very likely to end up with something that works. It will not scale really well, but it will work. The problem is that the spec never says why you do these things. There's a long list of rules. And so if you stray outside of those rules, you're a test pilot. You're in no man's land. So you have to, if you want to build a really scalable OSPF product, you have to really, really intuitively understand everything about the protocol before you try to do it, or it will fail in interesting ways, which makes it a barrier to entry in the high-end router market, which always worked for me. ISIS is a simple protocol, but it's in this arcane foreign language called ISO-speak. And if you learn the lingo, it's actually pretty straightforward, and it's a simple protocol. Plus, there's so much boilerplate on the spec that as the pages fall off, you won't hit anything important. So I actually have my original 1990 hard copy ISIS, which has lost a dozen pages off front and back, and I never worry about. That's great. And this is also a barrier to entry in the high-end router market because people look at the spec and go, ah. So once again, you have to know the protocol intuitively in order to be able to understand what the language is saying in order to go implement the simple protocol. Now there was a lot of shouting over the years about ISIS because it was an OSI protocol and it was going to be, you know, you'd have to go to foreign countries and sit in rooms with people wearing ties in order to make any changes to the protocol. As it turns out, OSI died, and nobody other than a few people cared in the IATF about ISIS. So in fact, it's really easy to extend because you get the same 10 people together in a room and you say, let's do this. Everyone says yes, and you print it and, you know, send out an internet draft, and people go off and implement it, and it's fine. This is a lot harder to do with OSPF because everybody's an expert, and you know, there's lots of shouting in the room and so forth. ISIS, because it is run in the biggest and scariest networks in the world, there's a tremendous amount of self-interest on the part of the vendors to make sure that it really, really works. And when it gets extended, the extensions happen quickly, and they're happening because they're necessary, not because they're fun. So things tend to happen quickly, they tend to scale well, they tend to be stable quickly, because everybody's screwed if the implementation is bad. OSPF is fairly difficult to extend because it wasn't designed to be extensible. And in fact, people were very proud that this is, by God, an IPv4 only protocol, and IPv4 will be great for the rest of eternity. And then IPv6 came along, so they had to start over. So there's this whole thing, it's called OSPF v3, and it has, you know, unless you step back from it, it doesn't really look very much like OSPF v2. So if you want OSPF for IPv6, you're going to have to wait for your vendors to sit down and implement a protocol that's even more complicated than the last one. ISIS, the encoding is pretty simple-minded, but as it turns out, it's easy to extend, and so you know, coming up with the IPv6 spec change for ISIS is a weekend project. You know, and coding it is probably, you know, a 2-week project if the rest of the IPv6 stuff is already in place. And as it turns out, it was IPX ready as well. And somebody talked about extending it for Apple Talk once, but that never happened. OSPF was optimized for things that don't matter. And there's much paranoia about using link bandwidth, which when the internet was made out of 9.6 links probably made more sense. The CPU alignment, you know, when you had 4.77 megahertz 8080s, 8088s, you know, maybe it mattered moving all those bytes around, but none of that matters anymore. ISIS is optimized for things like large LANs and a cheap SPF, and none of those things matter anymore either. So there's all these great optimizations that are really complicated and they don't matter, but we can't get rid of them. And this shows the fallacy of early optimization. It's true in software and it's true in protocols. If you're going to deploy this, it's probably a lot easier to find people that know about OSPF. There's lots of books and you know, lots of wonderful, you know, seminars you can go to, and everybody knows about OSPF. And it uses words like packet that everybody's familiar with. ISIS, on the other hand, is well understood in this niche, and people are very comfortable with it in the large ISP market. And people have demonstrated that they can build really insanely large networks with it and that they work. So if you're trying to decide, well, which protocol should I use, these are things to consider. At the end of the day, other than that crazy full mesh case, the protocols are pretty much the same in terms of what they do and how they scale. So trying to choose one or the other by technical means only, it's a wash, you know. And stability and scalability really boil down to how well it's implemented. You can build wildly unscalable implementations, or worse, implementations that work until you reach a point and then they fall off the cliff, which is the way these protocols usually fail. And that's no fun at all. But it's not the protocol design ultimately that drives that. The biggest factor is probably, you know, what are you comfortable with? How do you want to design your network? Who can you find to run your network? And have they ever heard of ISIS before? If not, maybe you should probably use OSPF. There's been some question about, do we really need 2 protocols? And in fact, as time has gone on, they've become more and more the same. But since they're more and more the same, the irony is that nobody wants to switch because there's no motivation to switch, because they do the same thing. And there's entrenched constituencies of people that are running them. They've deployed the network, and changing them in the middle of the weekend, you know, on a Saturday night because you want to switch protocols. People do it, but it's not really very much fun. And as long as there's 2 protocols, you'll never get everybody to agree on which one they want. And not even the demise of IPv4 will help, because there's already V6 versions of both protocols, and people will continue to argue. So they'll never go away. They're both over 10 years old. They're getting a little long in the tooth, but they still work. And the graph theory they're based on goes back to assembly lines and system theory, in the 50s. There still works in progress even after 10 years, which is, testimony to their longevity and their extensibility within the area that they're being extended. Diversity is a good thing for a lot of reasons. You get cross-fertilization, you get, divergent opinions on things which have proven to improve both protocols along the way. And of course, it's job security. There's twice as much to know, so we'll all keep our jobs. Use the one that makes the most sense. It's ultimately what it boils down to. There's no magic right answer. They both probably make sense to everybody, so use the one that you're most comfortable with. That's it. Thank you. Do you have time for questions? Anybody bursting with a short question about their IGPs? We're late. Okay. Oh, okay. And tell if people are heading for microphones or not.
Can you comment about using both in a network?
Using both in a network. People have used both protocols in a network, usually when they're transitioning from one to the other. So you turn them both on and you set the administrative distance or preference of one higher than the other. People have used multiple protocols to get administrative barriers or to or to get three-layer networks and scary things like that. Ultimately, you have to be really, really careful with your route redistribution, like you do whenever you do redistribution. Mutual redistribution is really dangerous. So try not to do things like that unless you feel you really have to, and then ask your vendor, and they'll try to talk you out of it. Yes?
Chris Figotero, Zone Technologies. How many network prefixes do you put in your IGP?
How many network prefixes do? Well, I'm a vendor, so I don't run a network. So I have seen, typically thousands in the large ISPs when I've gotten a chance to poke around inside them. I've seen one multi-area OSPF that had about 2,000 summaries and 70 routers in the area that I could see in the router that I had a picture of. I've seen lots of redistribute connecteds, or its Juniper equivalent, at the edges of large networks. So you see a couple of thousand sort of stubby things around the edges. People try to eliminate that stuff or to summarize it as best they can. And at those levels, all of the implementations seem to chug along just fine. And once again, it's not the number in there that's the real issue. It's the topology is where the scalability gets interesting. Anybody else? Oh. Hi.
What's the distribution of deployment of distance vector protocols like EIGRP, which is Cisco proprietary, versus ISIS and OSPF? I know distance vector are more likely to be in enterprise networks. Are they also in small ISPs? Or
I've seen people using RIP in small ISPs, and it's usually because they have certain vendors' terminal servers that don't support better protocols. The problem with traditional DV protocols is hold down. And I once was dialing into an ISP in Santa Cruz and switched phone numbers and went to the other router. For some reason, I didn't have any connectivity for 3 minutes. And I said, "Oh, they're running RIP." There are people that use RIP for sort of edge connectivity things and redistribute it in. But to my knowledge, most sizable ISP and most people in the ISP community are using a link state protocol. EIGRP, if you're an all Cisco network, you can use. It has other interesting issues that I could talk about over beer. But it's a Cisco only, and so there's a lot of pressure for people to back away. And there aren't very many ISPs, particularly since unless you have all Cisco terminal servers in the whole 9 yards, then EIGRP is a non-starter. We can take one more. Go ahead.
There didn't seem to be much in the scalability issues between ISIS and OSPF, and yet you said ISIS is widely used in the large ISPs. Why is that?
Well, I touched on it a bit on the history. Part of it is an accident of what the state of Cisco's implementations at the time the large ISPs were choosing. That was really the driver for how ISIS got a foothold. Then it sort of snowballed because people saw what the other guys were doing and wanted to do the same thing because it seemed like it was working. And ultimately, the full mesh issues became an issue, but it was sort of an issue after the fact because they were already running ISIS in the few networks that they had this topology. And so it was yet another reason that you could never possibly switch. But other than that, it's mostly an accident of history. Thank you very much.